Hello everyone. So in this video lecture we will discuss a few problems of gaseous state based on JEE preparation. Okay, so we will try to solve a variety of problems covering different important topics of gaseous state. So let's start with the first problem. In this we have a vessel that has nitrogen gas and water vapor at a total pressure of 1 atmosphere. Now the partial pressure of water vapor is given to be 0.3 atmosphere, and when the contents of the vessel are transferred completely to another vessel having 1/3 the capacity and temperature is kept constant, we have to find the total pressure of the system in the new vessel. So for this, the first thing that we must know is that the vapor pressure depends on two factors. Vapor pressure of a liquid depends on temperature and nature of liquid. It means that right now whatever vapor pressure of water is, that is if it is 0.3 atmosphere, if the temperature is kept constant and nature of liquid is also same, so the vapor pressure will not change by changing the volume. Okay, so we can say that initial vapor pressure of water is equal to final vapor pressure of water if temperature is constant. Okay, so that's the main point in this question, that the vapor pressure of a liquid does not change as long as the temperature and nature of liquid are not disturbed. So now we can say that initially the container that we have, suppose this is our container, so in this P total is equal to pressure of water vapor plus pressure of gas, so that is given to be 1.0 atm. So if pressure of water is 0.3, then pressure of gas is 0.7 atm. Okay, so now we transfer it to another vessel having 1/3 volume. So when volume is V by 3, pressure goes to 3 times. Okay, it's just Boyle's law, that if the temperature is kept constant and the volume is 1/3, the pressure will be 3 times. That is PV is equal to constant. You decrease the pressure, volume will increase to keep this PV constant. Okay, so simply we can say that the moment we reduce the volume to 1/3, the pressure of the gas will be 3 times. So new pressure of gas is equal to 3 times its initial value, that is 2.1 atmosphere. And we know that the water vapor will exert the same partial pressure, so total pressure of system is pressure of gas now plus pressure of water vapor, that is 2.1 plus 0.3, that is 2.4 atm. Okay, so that's all about this problem. Let's move on to our second problem. Okay, so this is the second problem. We have been given a particular flask that contains ammonia gas and which is connected to a U-tube manometer. So initially the U-tube manometer has no difference in the mercury levels. That is, we can say, because this U-tube is open on one side, so atmospheric pressure will be acting from this side, and the pressure of nitrogen gas particles will be acting from this side. So if the level in the U tube manometer is same, so that is indicating that pressure of NH3 gas is equal to P ATM initially, means system is at equilibrium. Clear? So initially we know what is the pressure of ammonia gas. Now after that there was a sparking in the flask and the ammonia gas started dissociating. So after the partial dissociation of ammonia, according to the equation, that is 2NH3 gives you N2 gases plus 3H2 gases. Now they have used the word partial dissociation, means the entire ammonia didn't dissociate. So let us say if the initial pressure of ammonia is 2P, okay, and before dissociation the N2 and 3H2 were not formed. So this is the condition of before dissociation. Now after dissociation, if there is a difference in pressure of ammonia, okay, so 2P minus maybe P dash, so N2 will be P dash by 2, because when 2 moles ammonia are dissociating, 1 mole N2 is formed, and pressure is directly proportional to number of moles according to PV is equal to nRT. So if P dash is a decrease in the pressure of NH3, then increase in the pressure of N2 will be P dash by 2, and similarly the increase in the pressure of H2 will be 3 by 2 P dash. Okay, because 2 moles are generating 3 moles, so 1 will generate 3 by 2. So now if we can see the total pressure after dissociation, will be 2P minus P dash plus P dash by 2 plus 3P dash by 2. That is the partial pressure of all the components. Okay. So it is 2P plus P dash. Now we can say that the final pressure is greater than initial pressure. Initial was only 2P. Okay, this is the initial pressure, and after dissociation we have increase of P dash. So this is the amount by what the pressure has increased. Now this caused a difference of 6 centimeter in the mercury level in the two columns. So we can say that the 6 centimeter level rise is due to this additional pressure of P dash. So P dash is equal to or equivalent to 6 centimeter of mercury. Okay, so now we know that P dash equal to 6 centimeter of mercury. So what is the partial pressure of H2 gas? Partial pressure of H2 gas at equilibrium means after the dissociation was complete, the partial dissociation was there and system again came into equilibrium, then the partial pressure of H2 we have written it is 3 by 2 P dash. So it is actually 3 by 2 into 6 centimeter of mercury, that is 9 centimeter of mercury. Okay, so that is the answer. So let's now move on to our next problem. So in this we have decomposition of Cl2O7 to give Cl2 and O2 gas, and this is also partial decomposition. So even after the decomposition, Cl2O7, Cl2 and O2, all three gases will be present in the reaction mixture. Now this partially decomposed mixture is allowed to effuse. Okay, what is effusion? When you allow, suppose you have a balloon, okay, and you just prick it from some point, then gases will start moving out. So that escape of gases through a pinhole opening is called effusion. So when this reaction mixture is allowed to effuse out through a pinhole, the gas coming out initially was analyzed, and in that gas, the mole fraction of O2 was found to be 0.6. Okay, so when we talk about the effusion, in this mixture we have Cl2O7 plus O2 plus Cl2. So all three components are there, but when the effusion starts, it's not that the all gases will come out with the same rate. It is possible if O2 has more number of particles, then definitely the number of particles of oxygen coming out per unit time means their rate of effusion will definitely be higher. So rate of effusion depends on how many molecules of that particular gas are present. Okay, so when this effusing gas was analyzed, it is found that it has a mole fraction of O2 that was 0.6. So it means the mole fraction of combined Cl2O7 and Cl2 was 0.4 and of O2 it was 0.6. So now we have to find the degree of dissociation, that how much of Cl2O7 actually decomposed to give Cl2 and O2. So let us say we started with 1, 0, 0 initially, and after some time 1 minus alpha 1 mole, so it is alpha, and if you balance the equation here, what will be the balanced equation? Cl2O7 gives you Cl2 plus 3.5, or you can say 7 by 2 O2, so it will be 3.5 alpha after the dissociation. So now let's assume that X is the mole fraction of Cl2 in the gaseous mixture. That is being analyzed. So if X is the mole fraction of Cl2, then what is the mole fraction of O2? It is given to be 0.6. Now we know that rate of effusion, rate of O2 divided by rate of Cl2 is equal to pressure of O2 divided by pressure of Cl2, mass of Cl2 divided by mass of O2. So this is the equation that we know, that rate is directly proportional to the pressure and inversely proportional to the under root of molecular mass. Higher the pressure of that gas within the system, faster it will effuse out, and bigger the particles of the gas, slower will be their speed, so their rate of effusion will be inversely proportional to their molecular masses. So from this, now we don't know what is the partial pressure of O2 and Cl2, but we do know that the degree of dissociations means from the degree of dissociation how much O2 and Cl2 are formed. If Cl2 have alpha particles, or you say 10 particles of Cl2 were formed, then definitely according to this equation O2 formed was 3.5 times greater than the Cl2. Okay, and pressure depends directly on number of moles. So if there were 10 particles of Cl2, then the particles of O2 were actually 35. So number of mole depends on particles and so do the pressure. So instead of pressure, we can directly relate it to the number of particles, which exactly depends on these values. So you can write it as 3.5 alpha divided by alpha into molecular mass of Cl2, that is 71, divided by molecular mass of O2, that is 32. So solving this, now how can we solve this? Because we don't know the rate of effusion. Now we have the equation on one side, the rate of effusion should be equal to this equation, and also the rate of effusion depends on their mole fraction. So this RO2 by RCl2 is also equal to proportional to their mole fraction. So it is XO2 divided by X of Cl2. Because more the number of moles, faster will be the rate. So rate of effusion is also directly proportional to their mole fraction. The mole fraction of O2 is 0.6, of Cl2 we have assumed to be X. Now these two terms can be equated because both are giving you the same expression. So after solving this, that is 0.6 by X is equal to 3.5 root 71 by 32. We get the value of X is equal to 0.115. Okay, so this X is equal to 0.115 is actually the mole fraction of Cl2. Mole fraction of O2 is 0.6. So what will be the mole fraction of Cl2O7? So X of Cl2O7 is equal to 1 minus 0.6 plus 0.115, that is 0.285. So now we know what is the mole fraction of Cl2O7 in the mixture. Now again we have to apply the same concept all over again, that is because we need to find the degree of dissociation. So for that, if we apply this rate equation once again, that is the rate of Cl2O7 divided by rate of Cl2. Now it will be, how many Cl2O7 are there? 1 minus alpha times, and how many Cl2 dependent on alpha. So it will be 1 minus alpha divided by alpha into molecular masses of Cl2 divided by molecular mass of Cl2O7, that is 71 divided by 137.5. So this rate is also directly proportional to their mole fractions. So what are the mole fractions? 0.285 divided by 0.115. So solving here, you will get your alpha is equal to 0.2. Okay, so now once again we can just go through the entire system. So initially we had Cl2O7 decomposing into Cl2 plus O2. Now, so we assumed X to be the mole fraction of Cl2. So for this effusion, the rate is directly proportional to their mole fractions, and rate is also equal to pressure divided by root of molecular mass. So we have two equations, so we use the values in two equations, equated those two values. From there we get the value of mole fraction of Cl2, and subtracting the mole fraction of O2 and Cl2 from 1 gives you the mole fraction of Cl2O7. Then we apply the same equation for Cl2O7 and Cl2. Okay, we can also apply the same equation for Cl2O7 and O2 also. Okay, anything. Either you take Cl2O7 and O2 or Cl2O7 and Cl2, because solving either one will give you the value of alpha. Clear? So now let's move on to our fourth problem. Okay, so in this problem, the given factors are number of moles is 1 of a van der Waals gas at temperature of 273 Kelvin. We always take temperature in kelvins. Pressure is given to be 600 atmosphere. and volume is 0.75, sorry, volume is 0.075 liters. Now they've also mentioned the van der Waals constant B, and we have to solve for the compressibility factor. So let's see that for 1 mole, if we write on the van der Waals equation, it will be P plus A upon V square into V minus B is equal to RT. So this is the van der Waals equation. Now in this equation, this is your P real, the actual pressure at which the experiment or that process is going on. This is the volume of container. Okay, so this entire expression, that is P plus A upon V square, is the P ideal, and this V minus B is the V ideal. That is how we can write it as PV is equal to RT when number of mole of gas is 1. So in this case, we are given that pressure is 600 atmosphere. When the pressure is such a high, so we can ignore this A upon V square component. So when pressure is very high, A upon V square can be ignored because it will have a very small value compared to the very high value of pressure. So what is your P ideal here? So P ideal is approximately 600 atmosphere. Clear? At very high pressure, now this V minus B cannot be ignored, because when the pressure is very high, volume must be very low. So in a very low volume, that is 0.075 liter, if 0.024 liter R, suppose you have a container having a total volume 0.075 liter, and in that the gas occupies actually 0.024 liter per mole, and yes, we are given 1 mole of gas. So out of this entire volume, this much is already occupied. So what is the free volume available? So free volume available will be a difference of these two. Okay, so that is the main thing. V minus B actually tells you how much volume is actually available, means total volume of the container minus the volume occupied by the gas molecules. Okay, so using this equation now, because P plus A upon V square is approximately P, so the equation reduces to P into V minus B is equal to RT. So from here we can solve the values. That is, this P is your P ideal. So your P ideal is equal to RT upon V minus B. Now substitute the values. The value of R. Okay, how do you put the value of R? R has three values: 0.0821 liter ATM per mole per Kelvin. It is 8.314 joule per mole per Kelvin, and it is approximately 2 calorie per mole per Kelvin. So whenever you are confused about which value to use, now see, the volume here is being given in liters. We have been given number of moles and the pressure is in ATM. So when the pressure is given in ATM, volume is given in liter, you will use this particular value of R, so that while solving in the PV is equal to nRT on this equation, the pressure will have units of ATM, R will also have units of liter ATM per mole per Kelvin. So when the units are similar, they get cancelled out. Okay, when the pressure is given in ATM and you are using 8.314 value, now this joule value will not be cancelled out directly with any other unit. you have to convert this joule. So it's better that we use that value which matches with the given units in the statement. Okay, so from this P ideal we can calculate R is 0.0821 into temperature is 273, volume is 0.075 minus B is 0.024. So solving this will give you the pressure of 439 approximately. Okay, so this is your ideal. Now when you talk about the Z is compressibility factor, that is PV by RT. Okay, so now this RT is not going to change because temperature is not changing, or you can say Z is also equal to P real upon P ideal. So real pressure is 600 upon ideal pressure is 439. So it will give you Z is equal to 1.367. So Z is greater than 1. Okay, so I think you can go through the problem once again and note if there's any doubt, you can just put it in the comments. Okay, so that is all for today. In the next upcoming video, we'll be doing 4 or 5 more problems on gaseous state plus a bit concepts. Okay, I'll be discussing the payload, what is a payload and how to calculate the payload, and a few problems based on the van der Waals equation and ideal and real gas behavior also. So thanks for your time. See you next time.